Okay. So I was looking at you guys' worksheets, and most of you all did a really great job. So that was fantastic. I posted up the worksheet with the answers. So the worksheet with the answers is on there. So I think what I'll do, what would be most helpful for you all, just for me to show you guys how it works in SPSS?
Maybe talk through like each answer too.
Do what?
Maybe talk through like each answer.
Okay.
Because there are certain parts of the questions I didn't know how to do, like the APA format stuff.
Okay. Okay, that is definitely something I could do. I have a whiteboard, so I could show you guys that. And in the video that I'm going to post, I'm going to talk about writing in APA format also. Okay, well, first, I'll go through the answers. How about that? So I will, I'm going to share my screen here. Let me pull up the worksheet. Worksheets, and here we go. Okay, actually, I'll pull up this one. Okay, so the very first one, because this was in two parts, using the same data in two different ways. So as I said in the chat, you guys needed to rearrange the data for the between subjects. So this first one was a between subjects, and the second one was a within. So both of them are one-way ANOVAs because they're single factor, multi-level designs. We have 4 levels here. And so when you do the between, as you guys saw on SPSS, are you guys seeing my screen? Did I share my screen?
Yeah.
Yes. Okay. Okay. So the first one is a between subjects. And so you just use the one-way ANOVA under analyze and compare means. You would do the one-way ANOVA, and then for the repeated measures, you're going to always do the general linear model and then go to repeated measures. And we're going to talk about these others. We're going to also use these univariate and multivariate ones when we get into ANOVA, but those are the only ones. That's it. So here in here we have the compare means, and we've talked about the independent samples t-test and the paired samples t-test, which is when you have a single factor 2-level design. The independent is whenever you have like a between subjects, and this is when you have within the paired samples. And then the one-way ANOVA, and then these 3. And those are the only ones you're going to use in this class, and probably for most things, unless you have a situation where you're using regression, which I hate regression personally. I know Dr. Godlaski loves regression. That's his jam. But regression is down here if you guys work with a professor that does that. Okay, so when we're doing the between subjects, we have to rearrange the data. Because it's between subjects, we have, instead of 30 participants, we're going to have 120. So we go over here to variable view, and we don't have to have a participants column, but we can. And then we can have drink type, and then we have reaction time. I like to take the decimals down to nothing because we don't have any decimals. Now for the drink type, because it's between, we're going to need to assign the groups. So here I'll do 0 for water. I'll do 1. Let's see, I'll do 1 for caffeine. I'll do 2 for half calf, and I'll do 3 for decaf. And one thing about this is called dummy coding, and you should always start with 0 when you do these. And there's reasons for that. There's some statistical things you can do, but you should always start with 0 whenever you label your things. So then you got to determine your measurement. You don't have to determine a measurement for participants because we're not going to be using it. But the drink type is nominal and the reaction time is scale. Okay, so what I'll do first, I will enter in the data. Do any of you all have questions about that yet? Okay. Okay, this is caffeine. And how you label the numbers is really up to you. It's pretty arbitrary. Yep. Okay, everybody with me so far? Okay, so now that we have this data entered, I'm going to go over here to analyze. I'm going to go to compare means. I'm going to go to one-way ANOVA. Our factor, our independent variable, is of course the drink type, and the reaction time is our dependent variable. Yes. So then I'm going to click descriptives so I can get my descriptives. And this is all I need under options. And I'm going to click OK. We can go over here to post hoc, and we're going to talk about the different ones. We're going to talk about the LSD. We're going to talk about the Bonferroni, and we're going to talk about the Tukey test. These are the probably the most common post hoc tests. I remember learning about all these other ones in grad school, and the only one I use out of all these crazy ones is the Dunnett. And that's the only one that I've used other than these three. So we're going to talk about these three, and that's what we're going to talk about in the class. So LSD, Bonferroni, and Tukey. You can check all those, and we'll talk about why you use some over the other, and then we'll hit OK. So now I'll share my output. Can you all see my output screen?
Yeah.
Yeah, okay. All right, cool. Okay, so here we got our descriptives. We see we have 30 participants in each group, and we get the mean for each of our groups. We have our standard deviation and our standard errors, and we're going to talk about confidence and what confidence intervals mean also. So then here is the ANOVA table. So this is the one that we needed to enter. So on that sheet where there was like the table, the chart, this is what you should have put in those boxes. And yes, there are some blank boxes because this is a between subjects variable. So do you remember when we talked about that equation? And how I said all inferential statistics use the same equation where it's like between groups plus error over the within groups plus error. This is what this is. So here's the between groups and here's the within. So here are the variables here. And we'll talk about these numbers, the sums of squares. This is a big thing I'm going to talk about is the sums of squares and where this comes from. We're going to talk about the mean square and what all this means and how we get to the F value. If you wanted to know already, just for funsies, so that this doesn't hit you as a shock, if you were to enter in the sums of squares and divide it by the degrees of freedom, then you'll get the mean square. And then if you get the mean square, if you take this mean square, which is the between groups, remember I said it's like that equation? If you take this mean square and you divide it by this within groups mean square, you'll get the F value. So that's the calculation that it's doing. And I'll talk about where these numbers come from, because this is where it all starts. You take this divided by this to get the mean square, and then you divide these to get the F. So the degrees of freedom, remember we have 120 participants, so it makes sense that our total would be all of our participants minus 1, because 1 can't vary. But the reason why these are what they are, the between groups, is because we have 4 levels, right? We have 4 levels. So one of those levels can't vary. So this is degrees of freedom of 3. And then for the participants, for the within, this is all of them together. So for this, we have 116 because of our 120 participants, we have 4 groups. So 1 participant in each of those groups can't vary. So you do the within groups minus 4. So that's why it's 116. And so here's our F value. And we have, this is our P value, our significance level, and it is less than 0.05. So we do have significance. Congratulations. So the ANOVA table, what it's going to tell us is it just tells us that there's a difference somewhere between the groups. We don't actually know where we're going to see a difference. So we come down here to our post hoc test to determine those. And I selected a bunch of tests. You might not have done this, which is fine. So we can look and we could see where our significance is between these levels. So we could see that we have water versus everything, caffeine versus everything, half calf versus everything. And you probably noticed everything's significant except for half calf and decaf. Half calf and decaf are not different from one another. But everything else is significant. So this doesn't tell us a whole lot, but we could come up and we could look at the means and we could determine, okay, so half calf and decaf are not different from each other. That makes sense since we're dealing with 14 and 15. Those are pretty close. But you can see that caffeine is 4 and water is 22. So that is telling us that on average, the people in our study that had caffeine in our group, their reaction time was a 4. So that's really fast. That's faster, significantly faster than all of the other ones. Water was a 22, which was significantly slower than all of the other groups. Half calf and decaf were similar, yet faster than water, slower than caffeine. And so if we're thinking about purely the interpretation of this, and this is going to be the same for the within, because the data is the same, is that because decaf was significantly faster than water, that suggests that there is a placebo effect. People are believing they're drinking coffee, so they're believing that it's going to make them better. This is further demonstrated by the fact that half calf is pretty similar to the decaf, which suggests that there is a placebo effect going on, because even have half of the caffeine, just the belief that you're having coffee is going to get you there a little bit. But then we do know that caffeine really does work to speed up reaction time because it's significantly faster. So caffeine is doing something, but you need enough of it to overcome the placebo effect. So that's how we interpret this. Now, many of you guys did your graphs wrong, so I want to show you guys how to do the graph. Does anyone have any questions or thoughts on that so far? Nothing? You have plenty of time. I'm going to draw this graph.
How did you say you got the number for the mean square within groups?
That is, so here on this ANOVA chart, you get the sums of squares, and I'm going to talk about this in one of the next lectures, is where these numbers come from. But you take the sums of squares, and you can do this calculation if you wanted to. Take this number and divide it by the degrees of freedom, and that's going to give you the mean square.
Gotcha.
So if you took 4977 divided by 3, that's going to give you this. And if you took this divided by 116, you're going to get this.
Okay.
And then if you divide these together, you'll get this F number.
Got it. Perfect. Thank you.
Yeah. And because this represents all of your random error, and this is all of our systematic error, right? Our confounds and our manipulation. We want this number to be larger than this one. That's the goal.
Okay.
Because that's saying that the difference between our groups is because of our manipulation or compounds, but hopefully we don't have any of those. And it's not due to random error chance.
Okay.
If that makes sense. Okay, so here's my, see, I'll do caffeine, half calf, decaf, and water. So for this first one, let's see, 20, 10. Okay. Caffeine would be something like this. Half calf, 15. Okay. Let me split my screen here. Okay. All right. Are we back? Hang on. For this, I gotta take off my background. Okay. So your graph should have looked something like this because it's between, and so we're gonna do a bar graph. Now it's opposite, sorry. So your dependent variable is always on the y-axis, and your independent variable is always on the x. So this is the way it always is. These little bars here are the standard error bars. Sometimes you'll see them like this because they kind of go above and below. And this is how much variance on average. So whenever you see these on graphs, which you guys have probably seen these on graphs before, these are your standard error bars. There were lots of people that graphed standard error separately. Standard error is just how much variance your mean is estimated from the population mean. So the bigger your standard error bars, the more variance you had in your data. So it gives you a little bit more information when you're looking at a graph. What questions do you have about the graphs?
So I know that there's a way in SPSS and SPSS to make the graph, but is there a way to include the error bars in SPSS, or should we just?
I don't think there is an SPSS.
Okay. Gotcha.
Sorry. Some people like drew it and posted it in there. Normally, if we were doing this in class, you'd just draw it. You can do standard error in Excel if you wanted to do Excel graphs. So, but I don't think there is a way to add the standard error bars in SPSS, but it will give you a graph.
I made a graph and it added the error bars in SPSS.
You did get it too?
Yeah.
Okay.
It's like a thing you can check to give error bars.
Awesome. Well, there you go. Okay. What questions do you have about running the between one? Are we good on that? Okay, so I'm going to talk about briefly, I'm going to talk about APA format and what that means. When you write, I'm going to write out a t-test and the f-test. Okay. So these are the formulas. This is the t-test formula and the ANOVA formula. In your t-test, when you run it, you only have 1 degrees of freedom value. And in the f-test, you have multiple. So this is degrees of freedom, comma, degrees of freedom. So this, the first degrees of freedom is your between, and your second degrees of freedom is your within. And then you put whatever the F value is, and then you put your P value. If your P value is less than 0.05, you can simply put that it's less than 0.05. If it's greater than 0.05, you could simply put that it's greater than 0.05. You don't necessarily have to put the exact value, but most people do, so that you know exactly what it is. Usually when it's 0, 0, 0, like it was in this particular example, then you would put less than 0.01. And remember that that's telling us that when we reject the null hypothesis, we have basically a 0% chance of committing a type 1 error. That's what that p-value is telling us. So again, this first degrees of freedom number is the between, and the second one is the within. And this is how you write that in APA format. And when you type it out, all of the stats symbols need to be italicized.
So for that, it would just be P and F that needed to be italicized.
Right. Yes. When you're writing in a paragraph, like when you're actually writing a results section, you're going to talk about the means. So you would actually say caffeine, and then you'd put, like, you'd write something like, you would do like, you'd actually write it in a sentence where you'd have caffeine mean equals X, standard error equals X. You'd have something like this, where when you're writing it, you would say, our caffeine group, and then you'd put immediately mean and the standard error, and you'd italicize those two, was significantly faster than decaf means standard error, half calf means standard error, and water means standard error. And then you'd put comma and you'd put your F value. And that would be your technical sentence. You'd put like this thing. Other questions about that?
The degrees of freedom for the T, like for question 2, would it just be 29?
Well, so this is an ANOVA. So you wouldn't use the,
Okay.
we're just showing you what the T was.
Okay.
Yeah.
Gotcha.
Yeah, so it'd still be the F.
Right. Okay.
For the post hoc explanation, the first time, do you only put the mean and standard deviation the first time you mention that group, or do you mention it in every? Okay.
Yeah, you can. I mean, you can mention it multiple times if you're writing a results section, if you're talking about different things going on, but yeah. Okay, so now I'm going to go over the within. I only have the free version of Zoom, so this is going to end in a few minutes. Do you want me to end the meeting and you guys come back for the within? Does that work? That way we don't get cut off.
Yeah, that's fine.
Okay. Well, I'll end this, and if you understand the within, which I know that's probably the one that most of you guys had trouble with, So please come back because I do want to talk about, I'm going to talk about some of those charts in there. Yeah, so maybe I could do it in 8 minutes. Let's see, if we get cut off, I'll start it again. You guys come back. How about we just do it that way? Does that work?
Yeah, that works.
Okay. All right, so here I'm going to go back into my SPSS. You guys see my screen?
Yeah.
Okay. So this time, I'm going to enter it in exactly like it is on the sheet because we're only going to have 30 participants. So I'm going to come over here and I'm going to have caffeine, half, decaf. I don't want any decimals. So this time I'm not going to have the values box done, and all of these are scale. And again, the participants one doesn't even matter. You don't really need a participants one, but okay. So then I'm going to come over here to the thing. Okay. I feel like I'm racing against the clock. Okay, so this is how you enter it in for the within. So we would only have 30 participants here this time. Okay. Questions so far about that? Okay, so since this is a repeated measures, we're going to do general linear model, and then we're going to do repeated measures. We're going to have drink type as our variable, or drink, however you want to do it. And we're at 4 levels. We add that in. And then when we come over here, we're going to move over all of these. And this is just a within. We're going to talk about mixed models later on. And this is where we would do these mixed models. So then we have all these options, right? We go to EM means, and we need to bring this over in order to display our means. And we check this box, and we'll talk about these different ones. LSD is fine. Then for the post hoc tests, we don't need to add any of those because the EM means is going to do it for us. So we don't need any of this stuff. We could check descriptive statistics here in the options. Okay, and we hit OK. So for the within, and this is going to be true throughout when we do this within, SPSS gives you a bunch of boxes that you don't need. And you could actually delete them. You could select them and hit delete, and they will go away. The one I really wanted to talk about, though, is this Malachi's test, this Malky's test of sphericity. In the video, when I talked about the t-test and I talked about the tests, the Levine's test, and how it was verifying that we had a normal distribution. Do you guys remember that? This is the same test for ANOVA. So this is testing, we have this assumption that we have a normal distribution. It's normally distributed. We have a normal curve. And when I talk about the F, I'll talk about how it's related to the Z-score, the standard normal distribution. We assume that we have a normal distribution. And this is telling us whether we have a normal distribution or not. Again, the null hypothesis is that we have a, the null hypothesis is that we have a standard normal distribution. So we don't want to reject the null hypothesis. So we don't want this one to be significant. If this one is non-significant, which as you can see, we can assume sphericity. So we look at this first line because you see all these lines here.
Can you share your output page?
Do what?
Can you share your output?
Oh, I'm sorry.
It's okay. Thanks.
Thank you. Now do you see it? Ah,
Yeah.
Thank you. Gosh. Okay. I forget you have to share every screen. Okay, so I'm talking about this box here, the Malky's test of sphericity. So you can see here that it's not significant. So then when we look at our tests of within subjects effects, this is the ANOVA box. We just look at this first line because we assume sphericity because this is non-significant. If this was significant, we would have to look at either the greenhouse geyser or the Hundfeld. These are really similar and they do different things. I remember learning about them in grad stats, but you can choose whichever one floats your boat. If you have a favorite one, you could just use it. It's adjusting for the fact that our normality assumption has been violated. But this is non-significant, so we can just look at severity assumed. So this is the line we're looking at versus this line. So even though this chart is bigger, and we don't need the contrasts. So again, you could just select these and delete them. Don't need the contrasts one. For this box here, it's this line and this line that you should have entered into that chart. So this is the same thing as the other one, our between and our within. Okay. So again, we have 4 groups. So this is our between degrees of freedom. Our degrees of freedom is different now because we only have 90 participants. So it's a little bit different. I mean, so we only have 30 participants. So that makes it a little bit different. So here's our F. Our F is going to be a little bit different because we have a little bit different things going on here, but it's still going to be significant. So then we can get our means here to make the graph. The APA format and everything else is the same, but this time your graph should have looked something like this. Caffeine, half calf. I'm trying to hurry. How much time do we have?
Less than a
Spend
minute.
a minute.
Oh no! Oh no! Oh my gosh! Less than a minute. Something like this. With the reaction time, and then the same thing with the standard errors. And that's how you do it within. Whew, crushed it, got done. When this cuts off, I'm gonna come back. So if any of you guys wanna come back, you don't have to. If you feel like you got your questions answered, come back and we can talk more about it. Yeah, so here's the pairwise comparisons chart. This is the same thing that was going on before. You can see the same thing is happening where decaf and half calf are not significant from each other, but the other ones are. Okay. What questions do you have in our 1 minute that we have left?
So why is it confirming your null if it's significant or if it's like a normal distribution? Can you explain that? That kind of confused me. Like,
Oh, this part?
yeah, like with that part.
Yeah. So we want our data to be normally distributed because we have to make different assumptions if it's not.